My name is Jim Cullafello, and I'm the Vice Dean of Academic and Student Affairs at the Ira Fulton Schools of Engineering at Arizona State University. It's my pleasure to welcome you to our National Academy of Engineering Grand Challenges for Engineering Speaker Series, hosted by ASU and sponsored by the Kern Entrepreneurial Engineering Network. This engaging speaker series will focus on the 14 Grand Challenges for Engineering in the 21st century. Esteemed speakers from across the nation will be sharing their expertise on these grand challenges and answering your questions. We are proud to be a part of the NAE Grand Challenge Scholars Program, preparing graduates to address these challenges. It's my pleasure now to introduce Dr. Ramakrishna, the Director of the National Academy of Engineering Grand Challenge Scholars Program Network, to share his welcome.
Hello, my name is Ramakrishna and I am the Director of the National Academy of Engineering's Grand Challenges Scholars Program Network. The NAE Grand Challenges for Engineering, identified in 2008 by a committee of the National Academy of Engineering, are 14 critical global challenges for engineering in the 21st century, united by the mission of continuing life on the planet and making the world more sustainable, more healthy, more secure, and more joyful. The Grand Challenges Scholars Program, inspired by the NAE Grand Challenges, reflect the rapidly evolving nature of engineering education. The goal of the program is to prepare engineers who not only have the necessary technical skills, but also the cross-disciplinary knowledge, entrepreneurial spirit, the global multicultural perspective, and a sense of societal mission needed to meet the global grand challenges facing humankind in the 21st century. As of November 2018, 65 institutions across the US and around the world have implemented this innovative educational program, and nearly 100 are getting ready to join the consortium of GCSP schools. We at the National Academy of Engineering are thrilled that Arizona State University has taken the initiative to organize this series of presentations that will highlight each of the 14 NAE Grand Challenges and provide this valuable resource not only to its own students and faculty, but to students and faculty from around the world. On behalf of NAE, I'd like to thank ASU and the Kern Foundation for making the presentation series possible. I'm eagerly looking forward to following how this series impacts and inspires the next generation to create solutions to our society's most daunting problems. Our best wishes for a successful series, and thank you very much.
Here at FSC at ASU. I will be your moderator of this event in our Grand Challenges Speaker Series. So it is my pleasure to welcome you and to thank you all for being here. Tonight, Dr. Nancy Cooke will describe 3 lessons learned in addressing the grand challenges as a human systems engineer. She will share how a trip to Medellin, Colombia, taught her how multiple disciplines can come together to use technology to address societal transformation. Following her presentation, you will all have an opportunity to submit questions for Dr. Cooke, and I will ask her your questions along with a few of my own. Dr. Cooke is a professor of Human Systems Engineering at ASU and directs ASU's Center for Human, AI, and Robot Teaming and the Advanced Distributed Learning DoD Partnership Lab. She received her PhD in cognitive psychology from New Mexico State University in 1987. She is the past president of the Human Factors and Ergonomics and recently chaired a study panel for the National Academies of the Enhancing the Effectiveness of Team Science. Dr. Cooke was a member of the U.S. Air Force Scientific Advisory Board from 2008 to 2012. Her research interests include the study of individual and team cognition and its application to the development of cognitive and knowledge engineering methodologies, human-robot teaming, cybersecurity, intelligence analysis, remotely piloted aircraft systems, healthcare systems, and emergency response systems. Her work is funded primarily by the Department of Defense. Welcome, Dr. Cooke.
It's a pleasure to be here. I'm really honored to be surrounded by all these Grand Challenge scholars. And today I'd like to tell you about, in the next 15 minutes, about 3 different topics. One is human systems engineering. A lot of people don't know what human systems engineering is. But then how can human systems engineering address the grand challenges? I think that the 3 lessons that I'm going to talk about apply not just to human systems engineering, though, but to all walks of life in engineering. And then I want to tell you about a story about a trip that I took to Colombia that I think illustrates these 3 lessons very well. Okay, so how many of you know what human systems engineering is? Some of you do, yes. Not many people do. In fact, most people stumble upon it when they're in college. But it's the perfect marriage of psychology and engineering. It also includes other disciplines like cognitive science and physiology, but it's all about taking human capabilities and limitations into account when designing products, systems, services, processes. Basically, we make technology work for humans. Now, why do you need to do human systems engineering? Well, because a lot of people think that the good design is intuitive, it's common sense, but clearly it's not. And this is only one example where we have an ATM that can only be reached by the tallest man in the world. If you walk around our world, you'll see many more examples of where it's clearly not intuitive or people wouldn't have done that. And so technologies and systems really need to address the needs and the concerns and the safety of people to be satisfying and useful. Okay, now that brings me to the NAE Grand Challenges. And as you guys know perfectly well, there's 14 of them, and I just have 5 of them listed here. Some of them are clearly related to human systems engineering, like advanced personalized learning, enhanced virtual reality. All of these clearly involve humans in the loop, and advanced health informatics. Other ones, maybe not so much. And I think that this isn't just unusual for human systems engineering. You might, as a mechanical engineer, electrical engineer, or so forth, think that, well, some of these don't have anything to do with my field. And I'm going to try to convince you that you're wrong. So how can human systems engineering, and really any engineering, address the grand challenges? What even does that mean? How can I help manage the nitrogen cycle or restore and improve urban infrastructure? So let me tell you about these 3 lessons learned. Number 1, focus on a problem. We have the NAE Grand Challenges, but certainly those aren't the only problems in our world. We're surrounded by big problems, huge problems. NSF has big ideas. One of them is the future of work on the human technology frontier, which is really pertaining to human systems engineering. But there's other societal problems too, and the one I'll be telling you about in Colombia is a different one, but yet it's a big problem. I think you should address any problem that you truly feel passionate about. So what is a problem-oriented focus bias? Well, first of all, we're at ASU. We have to do this. It's use-inspired research. We're all about that. But beyond that, if you're focusing on a problem and you tell people, I am solving the climate change problem, this gives your work relevance and impact to the person that you're communicating to. Instead of saying, I'm a biology major, you say, I'm solving this big problem. In addition, it advances science and engineering to work on real problems, but also it engages people. And I think I'm preaching to the choir here because obviously you guys are all about solving problems with the Grand Challenge Scholar Program. But I'll tell you a story about my daughter when she came to ASU, who's not, I'm not going to point her out. She's in the room, but I won't point her out to embarrass her. But she's very problem-focused, and when she first started at ASU, I said, well, what do you want to major in? Do you want to major in human systems engineering or biology or maybe law? And she said, no, none of that, none of that. I want to save the rainforest. So that is a problem, right? And so how did she solve that problem? What major did she become? She's almost ready to graduate. And she's a multidisciplinary major in biology, conservation, ecology, with a minor in law, ethics, and homeland security. So I think with that, that equips you to solve that problem and save the rainforest. Okay, so how can human systems engineering contribute to societal problems? Well, human systems engineers understand people. We understand a lot about people, their needs, their capabilities, their limitations. And we can bring all of this understanding of people to bear on complex problems that involve people. We also have different methods, measures of human performance, need, usability, cognitive and social processes. All of these methods and tools can be brought to bear on these big problems. So lesson number one is don't dismiss these problems that sound like they're out of your league. Don't dismiss the nitrogen cycle and energy from fusion problems. When we don't think that there's a role for human systems engineering, or maybe a role for your particular discipline, we likely do not understand the problem well enough. And this is an example from a committee that I was on for the National Academies. It was a study on high-performance bolting technology for offshore oil and natural gas operations. And there I am at a bolt manufacturing plant in Houston, Texas. And at our first meeting, I was surrounded by metallurgists and materials scientists, materials engineers, and I was the lone social scientist. And indeed, I was the only woman in the group. And I was wondering, what am I doing here? What do I know about bolts? What do bolts have to do with humans? Well, over the course of the study, I came to find out that they have everything to do with humans. From the time that they're manufactured, the time that they're inspected, installed in a rig, maintained, they come across humans every step of the way. And humans have pretty much been ignored in the equation, and they're causing a lot of variance in the system. So I finally got it, and I'm like, I just didn't understand the problem well enough. Okay, number two, take a human plus systems perspective. When we say human systems engineering, we really mean systems seriously. And so it's not just the human, but the human interacting with the technology in the context of a very large system, in the context of the environment. And there's many aspects of that system that we have to consider. And let me give you some examples. Here's a system that I've worked a lot with. It's the MQ-19 Operator Control Station. This is the Predator UAV ground control station. It has, I would call it a large socio-technical system, because it has lots of people, has a sensor operator, a pilot, I think there's some observers in there, and it also has lots of technology. So it's a large socio-technical system, and it's not a very good one, human systems engineering-wise. Each of these yellow stickies are problems, human factors kinds of problems, like it takes 22 keystrokes to turn on the autopilot. That's a problem. So this system was built by people who design nuclear power plants, not aviation systems. It was very foreign. It takes pilots like a year to a year and a half to learn how to use this system. And I talked years ago to one of the industry program officers, and he said, well, it's been about 10 years now since the Predator's been fielded, and it might be time to start thinking about human factors. And I said, no. And as a result, I mean, it was too late. We have these legacy systems. No one's going to go in and retrofit them. Hopefully the new systems, they'll think about human factors in the beginning. But here's the lesson here. Just when you think you're taking a human systems perspective, think bigger. So I showed you that socio-technical system that is the Predator ground control station. But really, it's embedded in a much larger system of systems. We have multiple ground control stations. Each of them are controlling multiple unmanned aerial systems, multiple predators, and the sensor feed from these predators is being fed into a distributed common ground station where you have lots of 20-year-olds poring over it, trying to exploit the data to say something meaningful, and then hopefully communicate that to people on the ground who are in harm's way. It's a very complex system. Making a change to one part of this system without understanding how it's all interconnected can lead to unintended consequences. So I think that these grand challenge problems involve big systems like this. And it is a challenge because of the system. Okay, number three, collaborate with other disciplines. This is the biggest one I think that we have. I was on, as Sarah was mentioning, on the committee for enhancing the effectiveness of team science. And what this was all about is learning that big problems, grand challenge problems, are not for the faint of heart, and they're not for the single investigator or even the single discipline. Gone are the days when you have one computer programmer sitting in his closet, typing up code. You are all going to be working with other people, probably people from other disciplines. If you use this systems perspective, that should help identify the kinds of expertise you need on your team. And what this graph is a graph showing the number of authors on various published papers in science and engineering over the years. And what it shows is that papers with 6 to 10 authors are accelerating, and that's the largest growing group of authors. So more and more, we're publishing papers with multiple authors, usually from different disciplines. We have a star of our field, Micah Ensley, who's a mother of situation awareness, and she has this thing called the Golden Triad, where she said the best way to do design is to have a human systems engineer working alongside other engineers and working with users. That's very important. You don't want to leave them out of the loop, or you'll design something that is not for the user. And so human systems engineers are kind of the glue between the user and other engineers. But lesson number 3 is team science is hard. If you've ever tried to do this, if you've ever tried to work with somebody in another discipline, it's sometimes like you're speaking a different language. You need to learn the other's perspective. You need to communicate how you can contribute to the problem, and you need to be able to communicate across disciplines. So this is very challenging, and that's a lesson that is learned. So how can we help? How can human systems engineering help solve the big societal problems? So this is a summary. Focus on the problem, and don't be afraid if you feel like the problem isn't meant for you. Take a human plus systems perspective, and then take an even bigger one, and collaborate with other disciplines, and be ready for the challenge. Okay, now let me switch over to this tale of, I call it a tale of 2 cities. It's really one city, Medellin, Colombia. I had the opportunity to go visit Medellin for an International Ergonomics Association meeting a few years ago. And while we were there, they took us on a very interesting tour of that city. Now, this is a city that back in the 90s you would not have traveled to at all, but they took us on a tour of the city and in some of the most poor neighborhoods of that city. This city is, I call it 2 cities because it's topographically separated. It's not like Beverly Hills, where the rich people live up in the hills. The poor people live in the hills, and the richer people live down in the valley. And when people immigrated to Colombia, the poor people found land wherever they could in the mountains, and sons and daughters built houses on top of their parents, on top of the grandparents, and they just kept going up the mountain. So there's a large topographical divide because it takes like 2 hours to hike down the mountain to get to this place on the bottom where all of the jobs are, where the education is, where the cultural activities are, where all the shopping is. And so there's really a separation between the haves and the have-nots. In 1992, Medellin was labeled the most dangerous city in the world. It was the murder capital of the world. In the 1980s, Pablo Escobar led a criminal ring. He was a drug cartel kingpin, and there was lots and lots of murders. The murder rate escalated pretty high in the early 1990s. In 93, Escobar was gunned down by police on the top of a Medellin roof, but that didn't solve the problem. They went on to develop new leadership in the cartel. That there were more and more murders, there was more gang warfare, there was guerrilla warfare. The whole group became paramilitaristic, so the problem got even worse. Then, and a lot of this is because of this topographical divide, too. In 2004, World Bank launched a program of transformation, and they did it with the help of lots of people, planners, designers, politicians, university professors, and even gang members. Remember, they're users, right? Users of this area, the gang members. And they started putting in botanical gardens, schools, and museums in the poorest of the neighborhoods. And not only that, this was what really fascinated me. And we went to this place that you would never go to in the 1990s. But they put in a metro cable transportation system that connected the poor and the wealthy. So they had cable cars running up and down the mountain. They had a metro system, a light rail system running up and down the mountain. And they even had outdoor escalators. So this was really fascinating. So now it only took 15 minutes to get down the mountain instead of 2 hours. When we were there, we saw even the dogs using the escalators. It was kind of amusing. They also put things called parque biblioteca inside the poorest neighborhoods. These were cultural centers where people could get on the internet, get educated, and they'd have certain classes. They could enjoy the things that people were enjoying down in the valley before. And then the gang members turned to expression through beautiful graffiti murals that were all over the neighborhoods. This is how they sort of released their tensions. And remember, the gang members were on the committee that decided to do this. When we were there, the gang members were very proudly displaying all of their graffiti murals. They used to be gang members, but they weren't anymore. And the homicide rate dropped, gang violence decreased, and unemployment decreased. It was really an amazing transformation, and when you think about it, it's by using technology in a way to connect people. Some of the lessons that were learned from this experience was architecture must never be a barrier to human interaction. Public and accessible urban services reduce inequality. Education drives change, and using technology as a means and not as an end in itself. So they didn't put the escalators in because they could. They did it because that would be a way to connect people. So Medellin was transformed. It was a new city now. And how was it transferred and transformed? This is sort of how I was inspired with all of this and these 3 lessons learned, because I thought about it and I'm like, well, they really focused on the problem. They didn't say send in the military. They didn't say send in more police. They said, what is the problem here? And the problem is this topographical divide. And they sought to solve that problem, not some other problem. And they understood the human system in a big way. And to this day, I don't know if any human systems engineers were on the team, but somebody was there that understood what the human issues were. And they also collaborated with others, including gang members. I think it was really crucial that the gang members were part of this team. And I want to say thank you, but before I stop, I do want to give you a commercial on the Center for Human AI and Robot Teaming. This is a center that was stood up in 2017. It's under the Global Security Initiative, and it's all about, I'm directing it, it's all about technology teaming with humans for global security. That's the problem we're focusing on. We take a systems perspective because we say it's not sufficient to just look at the human, it's not sufficient to just build a robot or an AI. You have to look at how the whole system fits together. So that's a system perspective, and we collaborate across disciplines with lots of people within and outside of ASU. We have 60 affiliates, and we have people from engineering, of course. We have people who do robotics and AI, human systems engineering, and law, ethics, but we also have artists, dancers on our team. So we're doing all the 3 things that I said. So focusing on a problem, looking at a systems view, and then collaborating across the disciplines. Thank you.
Thank you, Dr. Cooke. I hope that you all have learned something new about these grand challenges and are now as inspired as I am to learn more and to hopefully take some talent or action with regard to these challenges. So for the remainder of the time, we will give you, the audience, an opportunity to ask Dr. Cooke any questions that you may have about her work or the security field or anything else that you are curious about. So at this time, if you are joining us live, you may text your questions to the number provided on the program. If you are watching remotely via live stream, please add your questions directly through the YouTube chat. And we will do our best to answer as many of those questions as we can. So while you are all doing that, I will start us off with a few of my own questions. So what social or psychological implications exist for human-robot teaming? In other words, is there like a pseudo-relationship or a relationship component to this type of team structure?
Yes, definitely. So we think of it as a team. So we want to put robots and AI and humans on a team together. So it's a teammate relationship. So then you have to say, well, what does that mean?
Right.
What does it mean to have a teammate relationship? Well, what do good human teammates do? Good human teammates cover for each other. They understand something about the bigger task. They communicate well. I mean, you've probably been on teams where they don't work so well and some where they do work well. So we're trying to take the principles of what we know about teams, human teams, and apply them to these new heterogeneous teams, realizing that there might be some other model that's even better. I think also about the relationship between a human and a bomb-sniffing dog in human-dog teams. I think you can maybe look at those other models where they don't communicate in natural language, but they do communicate.
Right, yeah, there's a definite relationship there.
Yeah.
So switching gears a little bit, do you think it's better to differentiate technology that addresses national security and cybersecurity, or should they be combined when you're thinking about innovation in these arenas?
I think they're definitely combined. I mean, cybersecurity is part of national security, right, but there's also other parts of national security. There's sort of military and defense, but even climate change, as we're seeing, is part of national security. Right. I mean, people are migrating because of droughts and floods, and even people, I know people from Florida that have recently moved here because of hurricanes.
Mm-hmm. Absolutely. With regard to Medellin, what process do you think was the most productive in some of the early talks in terms of its transformation?
You know, I wish I could have been there to, or to find something that describes what process they went through. But I have to believe that I really was impressed by the fact that they brought in the gang members. And I think that was probably pretty important to get their perspective on things, because somehow they found out that there was this big divide and that the people who were living up on the mountain weren't so happy about what was going on down below.
Yeah, I thought that kind of resonated with me too. So what do you think exists currently to help stakeholders in general realize the benefits of the multidisciplinary approach you were talking about, team science, in terms of solving these grand challenges?
I know that there are a lot of programs now in universities that are trying to bring students together to form multidisciplinary teams. There's the report, the National Academy report that we wrote has recommendations for doing this very thing. There's a group called Science of Team Science that has annual meetings, and so they do actual research on what is a multidisciplinary team, how do you know when it's going well. I mean, really what we want is transdisciplinarity. That's really deep knowledge integration, not just having people from, say, 3 different disciplines in a room working together. You really want to be able to share knowledge and create new discoveries by integrating that knowledge. So there's a lot that we still need to learn to try to get over the challenge of that, but people are doing it.
So switching back to robot teaming, how does that particularly play a role in security, in addressing security? Is there anything that's currently available, or is there anything up and coming in the conceptual stage?
Well, I mean, it's just so pervasive in every walk of life. So certainly the Department of Defense is interested in human soldiers teaming with AI notepads and having unmanned tanks and things like that. But it's in all walks of life. So transportation, we could see it out in the streets of Tempe where we have driverless cars, driving around with cars with drivers in them. We could see it in medicine, manufacturing. We could see it, well, and even in cybersecurity, we need to have AI tools that will team well with the cyber analyst. So all of this, I mean, I think a global security initiative, we take a very broad view of what security is.
Right, right. And then so to kind of piggyback on that, moving forward, if it is so pervasive, what do you think are some of the ethical implications of robot teaming and security, or any of the grand challenges? Are there aspects of this collaboration of which humans should be mindful?
Yeah, definitely. So there are people who are worried about the robocalypse. Robots are going to take our jobs and kill us in the middle of the night. You know, I guess that's one scenario, but I think it's up to us to make that not happen.
Sure.
And that we need to, I think the more we can see robots and AI as teammates that are going to help us do the kinds of things that we don't want to do or that we can't do, and not so much to take over important decisions that we need to make. We leave that for us. So the decision, for instance, in the military to shoot is not yet being made by AI or a robot and probably won't for a very long time.
Right. Good. And what can other communities glean from the Medellin project in terms of creating safer cities?
That's a good question, and I thought about that a lot when we have some cities of our own that aren't too safe. And I've talked with one of Obama's, I'm blanking on his name, community-oriented policing task force leads, and he was talking about changing policing so that it's more community-oriented, so it's not about us against them, but you actually have people, not the gang members, but whoever's out there working to solve these problems as a united team and not to be us against them. So I think there are ways that you can go into some of these cities with some of these big societal problems and say, what is really going on here? How can we change the whole system to also change people's behavior?
Okay, so let's field some questions from the audience. How is human systems engineering implemented in renewable or alternative energy?
Well, certainly using renewable or alternative energy is a human behavior. And so if we want people to use renewable or alternative energy, we need to figure out how to change human behavior. How can we incentivize people to use it? How can we make them more familiar with it? I think those are all human systems engineering issues. And then when it comes down to it, there's even other issues about the energy itself or about the alternative. Is it easy to use? Is it something, because if it's something that people have to plug in every 5 minutes, they're probably not going to use it. So it has to be easy to use and easy to learn, and then people have to be incentivized.
They have to find the value and then still look at it as low cost in terms of time or implementation. You said that to focus on a problem, it is important that you are passionate about solving it. When and how did you discover your passions?
That's a really good question, and I do have an answer for it. So, I was in New Mexico, faculty at New Mexico State University, doing various research. A lot of it was on individual cognition. And then 9/11 happened, and that changed my life. I got really angry. I had children at home. The youngest was just 1, 4, and 8, 3 daughters. And I came home that evening after 9/11, and I looked at them, and I said, this should never, ever happen again. And what can I do? So I was very passionate. I think it was kind of like a mother bear thing coming out. But what can I do to keep this from happening again? And so that sort of turned my focus on national security.
Yeah, absolutely. Have you worked with electrical engineers in the Global Security Initiative? And if so, what research or positions did they take on in the initiative?
Okay, I have worked with electrical engineers, or more with computer scientists, but I've worked on a number of multidisciplinary teams, and not so much Global Security Initiative, because we're just getting started. I have worked with other kinds of engineers on projects in intelligence analysis, and how do you display lots of information to an analyst in order for them to make decisions and take some meaning out of the data. And so we play the role of, okay, what is it that they need to know? How can they use the visualizations that you're creating? How are they doing with this kind of display versus that kind of display? I've worked on other teams with some construction engineers where we go into a nuclear power plant and look at workflow in the nuclear power plant, looking at how do you measure some of the human teaming components of what they're doing. And a really interesting project that some of you may even be part of is a NASA project with Youngming Liu as the PI. It's about data fusion in the national airspace for next generation flight. And so what it's all about is taking large amounts of data from the national airspace, weather data, air traffic data, et cetera, fusing it together in real time and saying something about risk in the national airspace. Our part of it is taking data from the human part of that system. So we are monitoring in real time air traffic controller, pilot communications, and trying to say something about their state. So when they become overloaded, and we're the Polytechnic campus busy overloading retired air traffic controllers and looking to see what that looks like in their communication. And so it's a really interesting multidisciplinary project, lots of big data analytics and fusion people on it, as well as human systems engineering. So I think I found all of these different projects to be very rewarding and sometimes very challenging, but when you finally get it to work, it's fun.
What do you think is the current most important human factors challenge?
Well, I guess I'm biased. I think the most important human factors challenge is is looking at the future of work, what we're going to be doing in the future of life when we are working so intimately with AI, with robots. How can we make all of that work for us and not against us? I think working out that puzzle is one of the biggest challenges.
Absolutely. Can you comment a little more on human systems engineering's role in designing aerospace systems and aviation industry?
Oh, well, that's where human systems engineering got its start in the aviation industry, when planes started falling out of the sky because the knobs and dials weren't designed correctly, and pilots would, instead of doing the throttle, would do the landing gear, and lots of lives were lost because of poor design. So human systems engineering, or human factors, was kind of born in the aviation industry, trying to design cockpits so that they would be easy to use by pilots, and especially easy to use by military pilots when they're under duress. And right now, then we introduced automation into the cockpit with Airbus, and had lots of issues with that, because one misconception is that when you automate it and you automate the human out of the loop, everything's going to be great. Well, that doesn't happen. When you automate it, it changes the human's task. And in the case of Airbus, we also lost some planes then because the human wasn't able to operate or the automation wasn't doing what the human thought the automation should be doing. And take the Boeing 737 MAX 8 as an example. Okay, automation, but it didn't work the way it was supposed to, and people couldn't operate it. I don't think these are user errors; these are design errors.
Next question: are there any current or future projects like the one in Colombia that are in the works in other areas around the world?
That's a good question, and I don't know the answer to that. I hope that there are, because we certainly need them. There's a book that's coming out, edited by Rod Roscoe, Aaron Chu, and someone else, that's about using human systems engineering for societal transformation, for equity and inclusion. And there's lots of stories in there about people doing things like that, so that might be a useful source.
This is a multi-part question. Oh, no. What are the challenges of having a diverse team in transdisciplinary research? Does it take quite a while to come up with a problem statement, or is it the methodology? Kind of wondering which phase of research is the most challenging.
All phases. And a lot of it's just taking the time to try to understand the other discipline, and to try to understand what people really mean when they're saying things. So, for instance, I was working with an engineer on a project, and they said to me, "Hey, Nancy, we're going to do the experiment in your lab tomorrow." I'm like, "Okay, we're going to start the experiment in my lab tomorrow?" Because my experiments take about a year to completely run. They're team experiments. We have lots and lots of data collection. They said, "No, we're going to do it tomorrow." I said, "You're going to do the experiment tomorrow?" And they're like, "Yes, we're going to do it tomorrow in your lab in about 2 hours." I'm like, wow, that's different. And so I was kind of at a loss. I'm like, I don't understand what you're talking about. And I finally realized that at least this engineer, and maybe most engineers, when they say we're going to do the experiment, they mean we're going to do a demonstration of the technology. When I say I'm going to do an experiment, I mean I'm going to run hundreds of human beings through this human-in-the-loop simulator and look at their variability and have enough of them until I can say something meaningful about that variability. So it's really about communicating, and I think that's something that you can learn, but it takes time. It's sometimes really frustrating, but again, rewarding when it works out.
Is that kind of where your psychology background comes into play? Do you find that sometimes that particular experience helps you to kind of facilitate that communication?
Perhaps. I think too often when we're talking to people across disciplines, we assume that we know what they're talking about. And so I think that we have to do more of questioning of our assumptions when we're in that kind of situation.
Could you go into more detail about the bolts in the oil industry with relation to human systems engineering?
Okay. It was really interesting. I learned a lot about hydrogen embrittlement. And I didn't ever think I would need to learn that or know what that was. They talked about that a lot. They made jokes about hydrogen embrittlement, and I'm like, wow, it's not that funny to me. But as I went to these different bolt manufacturing places and talked to people who are in the oil and gas industry who used bolts and had to install them in these deep sea installations, I could tell that there was just a lot of human touch to the bolts. So the humans are there in the plant manufacturing the bolts, and they have to do certain measures and put things in, heat them to a certain degree. There's lots of room for making errors. I don't like to blame errors on humans because usually when they make them, it's because something was poorly designed. But when they install them, there's also lots of room for error. So every step of the way, they have to inspect the bolt. They have to take an undersea unmanned vehicle down and look at the quality of the bolt. So all of that involves human cognition and perception.
What is the overlap between biomedical and human systems engineering? And what might be some good examples of when biomedical engineers need to incorporate HSE?
Yeah, so biomedical or medical human systems engineering is just one application of human systems engineering. So I would say that there is some overlap between biomedical engineering, and the real question is to what extent does biomedical engineering take into account human systems engineering? We are proposing a joint degree now between human systems, or just in the beginning phases, between human systems engineering and the College of Health Solutions for that very reason, because there are a lot of people recognize that these two go together, and that human systems engineering can bring more of the knowledge of human capabilities and limitations, whereas the biomedical engineering brings more of the technology. And so I think it would be a good marriage.
Seems like a natural fit. Mm-hmm. What other stakeholders, like gang members, are often overlooked in product or solution design?
Well, user experience, which is also part of human systems engineering, is all about bringing in the users and doing user testing. But a lot of times people just assume they know what the user wants. And so it's not often done enough. I have a cool story to tell you that I was told by Dan Mote of the National Academies of Engineering about the need to bring in users early on, the need to pay attention to the users or listen to them. So in this story, a group of very well-meaning engineers goes to a small village in Africa and notices that the women are walking like 1.5 miles with big jugs to get water. And the water source was that far away, and so they assumed that's what they're doing. They're walking to get water, and they wanted to help them out. And so they built, over the next year, a really fancy pipeline that would take the water back to the village automatically. Came back later and found that the women were not using that pipeline. They were still walking to get the water. They finally talked to the users. They talked to the women and said, "Why are you walking to get the water?" And they said, "Well, this is the only time we could get away from our husbands." So they had a whole different reason for walking to the water that no one paid attention to. And a lot was wasted as a result.
A lot of money and work, and yeah. What are your thoughts on autonomous driving systems such as the ones used in Tesla vehicles? And how can human systems engineering help perfect these systems?
There's a lot of human systems engineering that's needed, but I think we're in a very dangerous transition phase right now between the time when it's just people driving cars, which is also not safe as we know, to the time when everything is completely automated, no people are driving cars anymore, everything is connected, pedestrians are connected and bicyclists are connected and highways are smart. I mean, that's sort of the nirvana that we're hoping for, and maybe that will be safe, but that's a ways away. In the interim, we have this really difficult transition period where there's some people driving driverless cars, there's people who aren't. The driverless cars are of different levels of automation. And the worst thing that's happening is that many of these vehicles require the human to intervene within like a quarter of a second. And we know that people aren't good drivers because it's a vigilance task, right? You just have to stare at the road for a long time and you're easily distracted. They want to do all kinds of things besides look at the road. And so now we're asking them to sit in a car that's automated and just watch the road, waiting for something to happen so that they can take over in a quarter of a second, and that's not going to happen. That's not a good model at all. So I think we need a lot of work, the human systems engineering end of things. There's a lot of automatic alerting systems that are being worked on. We have some people in our own program that are working on alerting systems and ways to wake the human up, but it's going to be a dangerous time in this transition, I'm afraid.
The growing pains.
Yeah.
How is studying and working in human systems engineering different from studying and working in human-computer interaction?
So human-computer interaction is like, that's actually what I thought I was going to be doing when I first started in graduate school. I was going to do human-computer interaction and get a job at IBM, which was the big thing back then. Human-computer interaction is part of human systems engineering. It usually deals with a single computer interface, looking at displays and controls. Now human-computer interaction is called user experience. So it's kind of the same thing, and they focus on usually single products. But there's other kinds of human systems engineering that focuses on transportation systems like driverless cars, focuses on aviation and the aerospace industry, focuses on healthcare systems. My focus is on teamwork and human AI robot teams and doing that for national security. So there's all kinds of applications that human systems engineering touches, and the single computer human interaction is just one small part of it.
Okay. So what are the end goals of human systems engineering?
A world where humans and technology are in complete harmony and you never want to hit your computer or your printer. You can be safe in transportation systems. You understand how to operate all of your devices around your house. You have smart homes that don't work against you. I have a partial, not a very smart home, but I try to sometimes turn the lights on and it won't let me because it's not time to turn the lights on. So these are all things that are working against people. And I mean, the whole idea is to make a safe world where people can function in a happy and effective way with the technology, not against it.
So as we're getting near the end here, I'd like to kind of return to end with a call to action, asking others to get involved. I'm sure that you have inspired some people here today to take action. So how can students or others get involved? What would be some first steps to addressing some of these challenges you described today?
I think if you have a problem that you're passionate about, I mean, let's say it's school shootings. That's a good one. Can you think about that as a whole system and think about ways that you might change behavior in that system? And maybe, if you're passionate enough, get together with people from other disciplines and start talking about this. Because I think story in Medellin was really an eye-opener for me. It was really a whole different way of approaching the problem. And that's what I think you have to do to solve some of these grand challenge problems, kind of think completely out of the box. And the best way to do that is with other people from other disciplines who can say, hey, have you thought about this? So,
absolutely. Or not always just agree with you. Maybe bring in some of the converse sides.
Yes.
So that's all the time that we have for today's event. Thank you for joining us tonight. Thank you, Dr. Cooke. Our next event will be Thursday, September 17th. It will be the same time at 6:30. It will be in the Marston Theater. So please check our website for more information on future events in this NAE Grand Challenges speaker series. Seriously. So if you would, please join me in thanking Dr. Cooke.